Hello and welcome to the videos for 1.3, or 10.3, I should say, transformations of functions. So we have talked about transformations once this year, so we've been introduced to most of these concepts. Therefore, this first video will be a lot of review. This year we've focused a lot on the vertical transformations or the rigid motions, but there is another type as well. So there's two types of transformations to a function. There's rigid transformations and there's non-rigid transformations. And you can kind of imagine from the names what types of transformations these are. Your rigid transformations, those are the ones that will not change the original shape. It will continue to have the same rigidity that it did from the original function. It'll look the same. It might just be in a different place. So a shift, a reflection, things that change position but not orientation. Then you've got non-rigid, which is the opposite of that. Your stretches, your shrinks, all kind of roped into what we call scaling. This first video is going to focus on what happens to go up and down. Okay, so we're not actually going to separate rigid and non-rigid motions. We're going to look at them together, but we're going to look at it more what affects your Y, your outputs, and what affects your X, your inputs. Okay, so our first three that we're going to look at are vertical shift, vertical reflections, and vertical scaling, of which we have two rigid and one non-rigid. All right, let's hop to it. Down here, example number 1. Use the function y equals f of x, graph below, to graph the following functions. Are they rigid or non-rigid transformations? We've got y equals f of x plus 2. We've got y equals negative f of x, and y equals 2 times f of x. So what we're going to do is give ourselves a nice big graph over here. We're actually going to graph these all together. Looking at the math here, these points go up to 5, but just in case, let's go up to 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. With a lot of 2 times, I took the 5. I said, hey, 2 times 5 is 10. Let's at least go 10. If we need to do more, I've got a little extra room on all the sides. So that's kind of why I chose 10. All right, y equals f of x plus 2. Now, f of x are these 4 points here. So if I'm going to look at this as f of x is equal to y, then the y that is being affected are the y's of these points, right? So if I'm looking at the y is f of x plus 2, I'm looking at y plus 2. I'm looking at a vertical shift. All of the y's in this function are going to go up 2 because it's a y transformation. So if I have the point 0, 1, instead of being 0, 1, it's now going to be at 0, 3 because it went up 2. Same thing for 2, 3. 2, 3 will now become 2, 5. Oops, let's try to make that a little more accurate. 2, 5. We also have 4, 5 instead of 4, 3, and 5, 5 becomes 5, 7. And so everything gets a vertical shift up 2. But notice it maintains its rigidity. It is the exact same looking. Now, I know my graph isn't super perfectly accurately straight, but it looks exactly the same as before. It hasn't been stretched or dilated or anything. All right, that was number 1. So we're going to go ahead and label this number 1. We should probably call these each their own function. So actually, I take that back. Let's not label it 1. Let's label this one g of x, label this one h of x, and this one k of x. We don't normally go with I of x. So this is g of x. All right, h of x is the negation of f of x. So we've taken it, we've multiplied it by -1. But again, that's -1 to the f of x's. In other words, it's -1 times the y's. And so what's going to happen? All of your y points are going to be negative this time instead of positive. Yes, if they were already negative, they'd go back to being positive, but they're all positive here. So 0, 1, remember, I'm not working off g of x, working off f of x, so the blue function here. 0, 1 turns around to being, I don't know, I'll do it in purple. 0, -1 this time. 2, +3 becomes 2, -3, and 4, -3, and then 5, -5. And again, we see that rigidity. This time when you multiply by a -1, you get a reflection, but h of x is still a rigid motion. It's still the same size. All right, with k of x, though, we're multiplying by 2. What's going to happen there? All of our y values are going to multiply by 2. So it's the same thing as if you multiply by -1. But instead of flipping over, everything's going to get a little bit bigger. So 0, 1 1 times 2 is 2, so that's going to go up here to, oh, pardon me. It's going to go here to 0, 2. 2, 3. Multiply 3 by 2, and you get 6. So 2, 6. 4, 6. And 5. Multiply 5 by 2, you get 5, 10. And there is a much more stretched out function. So even if my drawing is not super accurate, we can see how all of a sudden this orange one crosses the g of x function, which means it can't be the same shape, right? So it's definitely clear that this last function, this last transformation is non-rigid motion. So we can put a little n by that one, not a g, pardon me, an r and an r by those guys. Okay, those are actually the vertical. Okay, so let's try another one now, this time with an actual function. Graph f of x is equal to the square root of x and plot at least 3 points. Using transformations to graph g of x is equal to 2 square root of x minus 1. State the domain and range of g. Is this a rigid or non-rigid transformation? So a lot in this problem, but let's just start with that first one there. Graph f of x is equal to square root of x and using at least 3 points. Okay, got my graph here. Let's use some points first. Maybe I won't use y. Maybe I'll just write the square root of x in there. 0, well, maybe -1, 0, 1, 2. Well, that's awkward. This first one doesn't exist, right? So we don't want that one. Square root of 0 is 0. Square root of 1 is 1. Square root of 2 is hideous. So let's use 4 instead because then we get a nice 2. So see how that works? I chose 2 and I decided to change my mind. So I use those guys. I get the points. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 0, 0. 1, 1. And, ooh, that's really hideous. Hold on. Sorry. I'm going to have to redo that because that's gross. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 0, 0. 1, 1. And 4, 2. Man, graphing without axes is kind of hard. All right, so we've got f of x here. Beautiful. Now let's use transformations to graph g of x. So what transformations were we just looking at? What transformations did we see a moment ago? We saw that +2 raised it up 2. So having a +2 on the end like that is going to be a vertical shift. In this case, since it's positive, it's going to go up. If it was negative, it'd go down. Having a -1 on the outside, you multiplied, it flipped over. That's going to be a reflection over the x-axis. Multiplying by 2 scaled it. Since it was a whole number, it went up. If it was a fraction less than 1, it would scale it back, like 1/2. It would scale it down. In this case, it's a 2, so it gets bigger. So let's look at g of x now and see which function transformations we have in there. It looks like we have a 2 and a -1. That was my parent function, right? Timesing by 2 is going to stretch that function out, and subtracting 1 is going to move everything down. So let's do that. Let's take a look at what happens to our points. Okay, 0 times 2, still 0. 1 times 2, 2. 4 times 2, 8. Oh, I'm sorry. I used the x's by accident. 0, 2, and 4. Apologies. We want to multiply y, not x, Miss K, silly. Okay, so we get those, and now we're going to subtract 1 from each of them. So -1, 1, and 3. All right, so g of x is going to have those same x values, but this time it's going to be 0, -1, 2, 1, and out 4, up 3. And so we can definitely see that 2 stretch, right? It's definitely twice as big, and it's down 1. Beautiful. There's no negative in front of that 2, so we didn't reflect over the x-axis. All right, those are the x stretches, or the vertical transformations. The next ones, so those are all applied to the y. The next ones we're going to talk about are going to be applied to the x, and we're going to see horizontal transformations. A lot of the similar things. Luckily, yeah, I'll see you in the